So welcome back. Today we're going to talk a bit about elasticity, stress, and strain. Perhaps one of the easiest examples of elasticity is a simple spring. With the spring we have Hooke's law, which is the change in length being proportional to the applied force. Our K is proportional to the change in length. If we look at what happens when we're actually stretching that out, when we apply force, we're elongating it. It's very linear up until the point when it's not. In this region, we call it a plastic region. We're actually breaking down the material that the spring is made out of. The proportionality holds until the force reaches the proportional limit, the elastic limit. But beyond this elastic limit, the material just gets permanently deformed. Everyone's seen the slinky that's got that weird bend in it. That's sort of what's going on. And of course, once it's beyond this breaking point, the material simply breaks. So we have two things going on. We've got stress and we have strain. Stress on an object is simply the amount of force that you're putting in a certain area. Strain is how much you are changing the length of the object, either compressing it smaller or stretching it out longer or just deforming it to the side. We have something called the Young's modulus, and what that is the stress divided by the strain. If we take these three equations and juggle the E's and the F's and the A's a little bit, we're going to end up with this equation right here, where the force is equal to the Young's modulus times the change in length divided by the original length times the area, the cross-sectional area that we're talking about. In tensile stress, forces tend to stretch the object out. So this is tensile stress with our original object being yay big and then our new object being extended out just a little bit farther. You can think about a piano wire being stretched. That the piano wire is under tension. Compressional strength is the exact opposite of tensional strength. Things tend to get crushed down. You can think of columns in the great arenas of Rome. Those columns are under compression. Shear stress tends to deform an object. So it's when you're pushing one way on the bottom and the other way on the top. If you get a big book and kind of put it on your table and push one way on the top, and the table will hold it in place, so it's effectively pushing it the other way, and on the bottom you'll see it to deform sideways. When the stress becomes too great, the object is going to fracture. These three situations over here are fracturing objects. With tension, you pretty much get a rip at the weak point. Compression, you get a crumple at the weak point. And in shear, somewhere down there you're going to basically break across the object. If you think about bones that are breaking, if you break a bone and it's a tension break, it's not so bad to set it back together. Compression breaks are kind of worse because they end up with 3 or 4 pieces. Generally it'll break along fracture points and it's no good. Shear is about the worst of all. Shear is when you have compound fractures and you have bones jutting out of the body. Never good. So another thought on this, we've got bridges. So a horizontal beam bridge, it's going to be both under tensile and compressive stress. First, it's going to be tensile stress because we are going to have weight pushing down on it, and the bottom edge of this is going to want to stretch to either side, and it'll be under compression stress because the top is being pushed into the center. And straight beam bridges tend to be the weakest of all bridges, but they also tend to be the cheapest of all bridges, so you'll see a lot of straight beam bridges. If you build it with a big enough beam, then it doesn't really matter. So about 2,000 years ago, Romans started developing semicircular arches, and there are still a lot of these bridges sitting around today, 2,000 years later, so they're very, very strong. What they're doing there is you have a whole lot of force coming down. It's being translated basically into compressional force. It's probably one of the strongest types of bridges out there. The only problem with this is you can't exactly stretch these out for many, many miles like some of the great bridges we have today. So we should do a couple of problems. In this first problem, we're going to take a 1.6 meter long piano wire, which has a diameter of 0.2 centimeters. How great is the tension in the wire if it stretches 0.25 centimeters when tightened? So we have a Young's modulus equation problem. Here's our equation. We know everything except the area, so let's compute that real quick. And when we talk about area, we're talking about the cross-sectional area. So if we look at this piano wire and we're just looking at the cross-section of it, we're looking at the area that is equal to pi r squared, or pi times a millimeter squared, and that equals to approximately 3.14 times 10 to the negative 6 meter squares. If we plug all of this stuff now into our equation, we are going to end up with an actual force being put on that wire of 980 newtons. That's quite a bit of force. That's about another problem. Let's break this wire. So we've got the same 1.6 meter long piano wire. It has a diameter of 0.2 centimeters. What kind of force is it going to take to break it? So we'll look up the tension strength of steel in a table. There's a table in your book. We find that the tension strength of steel, the tensile strength, is 500 times 10 to the 6 newtons per meter squared. We can then multiply through by the area we just found a moment ago, and find out that in order to break this, it takes about 1,600 newtons of tension. So that's all I have for you. This is a pretty straightforward section. Thank you for watching, and please check As You Learn for the remainder of your assignment.